Hi, it's great to have you here. Today we are looking at a brand new problem, problem number 90, subsets 2. Let's break this problem down in a way that makes sense. The problem statement given to us is that we are given integer array nums that may contain duplicates. We have to return all possible subsets. It's also called the power set. So we are given an array and we have to return all possible subsets of the array. And the caveat here is that it may contain duplicates. We can return the result in any order. Let's look at an example to understand this better. So if you're given an array nums where the elements are 1, 2, and 2, the subset can be either 1 or 2 that are individually the elements themselves. It can be 1 and 2 and 2, which are elements 2 at a time. And then we have 1 to 2, which is all the elements. And then empty is also a part of the subset of the array. An interesting thing to note here is that 1, 2 can be generated in two ways. Either you choose this one and this two, or you can also generate the same subset by choosing this one and this two. So, and definitely we don't have two 1 2s here. We have just one. That means we cannot have duplicates. We'll use the race framework to navigate through this problem. So race is an abbreviation for reason, approach, code, and evaluate. Please look at the video in the description for a full explanation on the race framework. Without further ado, let's start with reasoning with the problem. Let's start with looking at our example once more. So we are given an array, the elements of which are 1, 2, and 2, and we have to create a subset. The subset can be empty, it can be 1, it can be 1 and 2, or it can be the following elements. If you look at this closely now, you'll notice here that there is one empty element, and then there are three elements where the prefix is 1, and then there are two elements where the prefix is 2. This is a nice observation to make. We'll use this observation when we look into the approach. So let's look at the approach. Let's see what the brute force will look like. One of the ways to tackle these questions is to choose our approach where we can make a decision on our elements one by one. So if you're given 1, 2, and 2, the indexes for which are 0, 1, and 2. So here we can start with making a decision with our 0th element, which is 1. So either we include it in our answer or we do not include it in our answer. We do the same. So this was our first level, which was dealing with the 0th element. On our second level, we'll take a decision on the first element where we either include the 2 in our answer, which is the first element, or we do not include it in our answer. We keep going and take a similar decision on the second element, which is also 2. So either we include the second element in our answer or we do not include the second element in our answer. We do the same here as well. So either we include 2 or we do not include 2. Similarly, we'll complete the entire tree. I went ahead and completed the tree for you. So what all that I added here is that on the right side, if you see, we'll take the same decision for each level here. So here for the first level, we took a decision on 0. On the second level, we'll take a decision on our first element. So either we include 2 or we do not include 2. And on our third level, we do say for this subtree, either we include 2, which is our second element, or we do not include 2. Similarly, for our empty result also, either we add 2 or we do not add 2. So after completing this tree, you'll immediately see that we got 8 elements of our subset here. So we got 8 elements, of which this is definitely one of the answers. This is also an answer, but then we see a duplicate here. Again, this is one of the answers. This is one of the answers. This is one of the answers. A duplicate. And this is an answer. So if we remove the duplicates, we should have only 6 elements in our answer. Now let's say if you were to improve this or maybe fix this and remove these duplicates, how would you do that? You'll have to probably sort your subsets each time, right? And then the second thing you'll have to do after sorting is remove the duplicates. One of the easiest ways to do that is use a data structure like set, which naturally removes the duplicates. Here, we'll still need to understand that sorting is not cheap. It's n log n. So in this case, if you're given n elements, the complexity will be n log n. And you'll have to do that for each of your element. So the total complexity will come out to be O2 to the power n. 2 to the power n because you are making two choices for each element. So if the array is size 3, so if n is 3, then you will get 2 to the power 3 elements, which is 8. You can check that here. These leaves, we have 8 leaves here. So how do we fix this? How do we avoid this extra sorting complexity and this set data structure to remove the duplicates? One way is that if you are somehow able to prune the branches where you are getting duplicates. So in this case, these are the two branches where we are considering duplicate cases. So if you are able to somehow prune these branches, we'll not have to deal with sorting and removing the duplicates via the set data structure. So how do we do that? Now we'll have to look closely at this tree that we have. So at each level, we are doing a call on the left where we include the element, and then on the right where we exclude the element. That's observation number one. The second observation. Here, if you see on the left where we include the element, all the results after that element that is in that subtree will have the prefix 1 and 2. So whatever is there in the parent, the subtree, all the elements of the subtree will always have that, because after including an element we always take the decision on the next element. So here the 2 that we added was our element at position number 1, and here on we take the decision on position number 2. Another way of saying that is, once I have made a call to my left where I've already included 2, which was at position 1, I want to make sure that when I make the call from to the right after considering 1, so from this part of the subtree, when I make a call to the right, I have to make sure that I never consider uh, the element which might be a duplicate, which means that if I've already considered 1, 2 as prefix, I want to make sure that when I make a call to the right, I skip all my duplicate elements, which is 2 here. Let's see how to achieve that. Uh, we'll add some metadata into the tree so that we know exactly how the recursion is working. And then I'll show you how to prune off the branches where the duplicates are coming. Let's look at the tree with some metadata. So this is the same tree, and I have pulled the element that was written here on the root. So if you see, so this element, I've just placed this element in the function. So if you think about a function bt, where the first element is I, the second is current, as current is where our intermediary results are being stored, and I is the element on which we are taking decision. So if you start looking at that, the first call that we'll start from is where I is 0 and you have nothing in your current. You go to the left, you go to the right. So if you just do it in the depth first search order, you'll go to the left where you will add 1 to our to your answer, and 1 is was our, so 1 was our 0th element. So we add 1 to our answer to the left. We further go left where I becomes 2, and you add the element 2, uh, sorry, the element 1. So you're here, you're taking a decision on element 1. You add that. You further go left. You move on to take the decision on element 3 on your level 3. So here your I is 3. You add the third element, which is 2, to your current. And as soon as your I becomes 3, that is where you collect the answer in your global variable. So in a similar way, it will go to the right. I will be 3. The element on the second position, which is 2, will not be added. So our current remains whatever it is. But since I is 3, our terminal condition will hit, and our intermediary result, which is 1 and 2, will get collected. So what now? How do we prune off the branches with duplicates? If you look closely, after making a left call, your I is 1, which is here. So after making a left call, your I will be at position 1, right? And when it goes to the right, That is where you look ahead and say that if the element in position I plus 1, if that element is same as my previous element, I will skip those cases. So, which means that you'll just compare, you look ahead here. So you'll just do a simple while loop and say, if my I plus 1 element is same as my current element, you will keep skipping. You will have to keep skipping those cases. So when you increment your I before making a right call, when you increment your I, uh, that is when you looked ahead and said that I see another 2, which is my current position, and you already have a prefix 1 and 2 here. So before making this call to the right, we'll increment I to 3. So this will be passed as 3 instead of 2. When that happens, notice that this is our terminal state. When that happens, this 1 will get collected in the answer. So we'll not essentially go here. We'll not go here. This will get collected and we'll prune off this tree. This answer will get collected, which is what we wanted here. And we'll never go to our duplicate case and we'll completely skip that. Another way of saying that is that I have already taken 2 into consideration here, where I am including and excluding it. I don't want to do that again, and that's why we skip that consideration here entirely, and we avoid our duplicate branches. When we look at the code, this will make more sense, but I hope that I'm able to impart the intuition behind this. It took me a while to really understand where are we skipping the duplicate elements here. And again, it is just before you make a right call, just before you make the right call, that is where you say, if the element that I'm about to see, if that element is a duplicate element, I don't want to consider that again. Okay, let's call this our optimal approach. And now let's move on to our coding section. Now looking at the code, so we are in code. So this is what the code will look like. We make our 2 calls to the left and right, where we increment the I, exactly what we did in the tree. We either include the element or we do not include the element. So this is very similar to what we did in our tree. I current, I gets incremented on all levels. So if you're going to the left, I gets incremented. Either we add the element or we don't add the element. So this function call is very similar. Nums is just our candidate. Other than that, it's very similar to what we just discussed. But you might come back and say, hey, I do not see the logic that we were just discussing, right? I do. So this logic of before going to the right, where you have to check for the duplicate, you do not see that logic, and you're correct. This right now does not have that logic. So this is our brute force solution that we talked about in the starting. This is our complete brute force solution, where after you have created subsets, you'll have to sort and you'll have to remove the duplicates. This solution is also the exact solution which works for the subsets problem. So there is another problem called subsets. You can use exactly this solution. Okay. Another thing that you might notice here is that we are sorting the array. Now, of course, I did not remove this part, but here we have to sort the array so that all the duplicates come together. Once those duplicates come together, so that's what we'll have to do. So this is like 1 n log n cost that you'll have to invest in, but you'll have to sort the array once. Once it's sorted, all the duplicate numbers will come together. And now we'll look into exactly how we'll skip those duplicates. So here is the code, which includes the snippet, which helps us skip the duplicates. If you just quickly compare, I put it side by side so that we can easily compare. Uh, they're exactly the same piece of lines, same calls. And just before we make the call to the right, we make sure that we skip if we have duplicate elements. Let's call this our optimal solution, which works for subsets too, which is this problem. So if we quickly dry run this for our example use case where I was 1, so when I was 1, it'll check if the element on the second position, so our given example was 1 to 2. So when I was here, it'll check, look at this next element. If it's the same element, I gets incremented. So here I will go to 2, and then since in the next iteration it will see that I plus 1 will become 3, so this condition will exit our loop. Here what will pass is I3, and our current, if you remember, was 1. So when this gets called from here, a terminal condition will hit, I is 3, and our answer will get collected. And this is how we'll prune this entire call stack, and we'll just collect the answer over here. I hope that is clear. And if you have any confusion, please look at the last approach section more carefully. I'm sure you'll get it. So now with that, we come to our last section called the evaluate. So looking at our complexities, um, the time complexity here will be uh, big O of 2 to the power n. So 2 to the power n we'll have to do that because we are generating all the subsets in this case as well. We can easily have a case where we'll not have duplicates. We have all unique, and in that case, we'll be generating all the subsets and we'll not prune anything. The space complexity here. So the space complexity here will be O of n, because at any time you'll have a call stack where you will have at the maximum of n entries, because we are taking a decision for each element, and at once you will have entries equal to n, and that's pretty much what you'll have for your space if you consider the call stack. If you are in an interview, definitely mention that we have a current variable. So this variable, this will also grow with the length of n, because we keep appending to this intermediary variable. And it is really important because here we are not cleaning up our variable. If you see, in at each state we are using it as a temporary state variable at each node. So it's very important to consider this, because as we'll go and look at other backtracking problems, cleaning this variable will take priority, because if you don't do that, your solution will run into memory limit exceeded, which is MLE. So we'll look at that probably in the next video. But this is another very important point to note, and this truly unlocks the power of backtracking, where we make sure that when we backtrack, we do clean our variables and we do not take too much memory. And that's a wrap. Thank you so much for joining me today for looking at this question. I hope that I was able to explain how the duplications are removed in this question. It's very, very important. Sometimes if you're in an interview, your interviewer might really ask you to stress upon this point. They've really started doing that these days, especially with agentic assisted coding platforms. So they really want you to understand how the recursion tree is being created. And as you know, the bigger companies are flying people in so that they can really check these minute details. So definitely I encourage you to go relook at this video, especially the approach section, and create a few of your trees by hand, see how the pruning will happen. You do that for 1 or 2 trees and dive in this code. I'm sure you'll be able to understand and internalize this well, positioning you great to be able to explain this in an interview. Thank you so much, and see you in the next one.